Hi, my name is Justin Wag and my partner is Corey Mitchell. For our final project, we tested the effects of multipath on various transmission methods. We used a Faraday cage to simulate the channel and multipath effects. We swept the frequency from 905 MHz to 925 MHz, and we tested the fidelity of three modulation techniques: 16 QAM, QPSK, and BPSK. As far as specific methods, we use the WinIQ simulation software to generate various signals and modulation types, and then we use the vector spectrum analyzer to demodulate the signal into its constellation diagrams. Here is just a basic block diagram of the testing methods we used. Our goal was to produce a deep channel fade using multipath effects somewhere within our frequency sweep. We managed to create one at 911 MHz, and the fade is about minus 65 dBm, where the average signal power is about minus 45 dBm. The first modulation method that we tested was 16 QAM. It transmits 4 simultaneous bits, resulting in a symbol rate of 1 MHz and a bit rate of 4 megabits per second. Here are the 16 QAM spectrum screen captures from the vector spectrum analyzer. As you can see, the signal power is just barely above the noise floor. As we move further away from the channel fade, you can see the signal power steadily increases. Here are the 16 QAM constellation diagrams. As you can see, the red dots represent the bits transmitted, and the green lines represent the transitions between those bits. As you saw, the closer we were to the channel fade, the more likely there were to be bit errors. As we move further away from the channel fade, you can see the signal fidelity goes up. The second modulation method that we tested was QPSK. It transmits 2 bits simultaneously with a symbol rate of 2 MHz and a bit rate of 4 megabits per second. We were able to demodulate the signal at a significantly lower frequency than the 16 QAM technique. These are the spectrum captures for the QPSK signal. As you can see, the signal power is even closer to the noise floor than the 16 QAM case, yet we were still able to demodulate the signal. These are the QPSK constellation diagrams. As you can see, even at that low frequency, the signal fidelity is still intact. As we move further away from the channel fade, you can see the bits move closer together, resulting in better signal fidelity. The final modulation technique that we tested was BPSK. It transmits 1 bit per symbol, which results in a symbol rate of 4 MHz and a bit rate of 4 megabits per second. Using this method, we were in fact able to demodulate the signal at the center of the channel fade. As you can see from the BPSK spectrum captures, there's nearly no power in the carrier, and the spectrum is barely above the noise floor. These are the BPSK constellation diagrams. As you can see, the signal fidelity is still intact. Ideally, these constellation diagrams would only have a left to right orientation. This vertical component can be attributed to noise in the channel. When comparing the various methods, we can see the 16 QAM method has a very high bit rate. Using pulse shaping, it also has a lower bandwidth requirement. On the downside, it has very low resilience to noise and a higher chance of bit errors. The PSK methods have high signal fidelity, very resistant to noise, but they are lower bit rates and higher bandwidth requirements. These experiments serve to further reiterate the trade-off that must be made between signal fidelity and bit rate. As far as improvements, the 915 MHz band is not optimal for multipath effects. We would be able to see many more multipath effects around the 2.4 GHz band where most cell phones operate. Another improvement would be to test bandwidth requirements. Obviously, the choice of modulation technique often depends on the bandwidth requirements.